right, so let's keep going with Notebook 3. So you'll remember last time we were looking at the problem of wanting to classify the sentiment of movie reviews. And we're going to be doing it in this notebook with Logistic Regression, Naive Bayes. And then in Notebook 4, we'll get to see how to do this with neural networks. So it'll kind of be two different, very different approaches for the same problem. And last time we were really talking, and it's really important to kind of understand how your data is set up and what we have kind of these different methods and dictionaries for using it. And so I just wanted to look at that again briefly. So here, this has been processed into tokens, and we have a number of kind of these special tokens, such as XX for an unknown word, beginning of string, or beginning of the text, repetition, that the next word begins with a capital letter, and so on. And then can anyone tell me what I2S does or is? Louder? Into string. Yeah, so that's going from an integer to a string. And why do we need to go between the two? Yeah, and I'll repeat that for the microphone. So for the computer program, you're often using integers. That's how we kind of are indexing our tokens. Anything human-oriented, you want to see the string so that you both can understand it as the programmer. Also, the original was in a string, and so we're kind of converting it to integers to make it easier to work with, but sometimes we'll want to switch back. And so we had I to string and also string to I. And what kind of data structures were I to string and string to I? List and dictionary, right? So I to string is a list because you don't actually have to store the integer. It's kind of implicit in the list of the order it's in, whereas you need a dictionary for string to I to be able to look up a string as a key and get back an integer as your value. And so here we saw, saw part of the kind of dictionary, string to I. We created the term document matrix ourselves using a sparse matrix in SciPy. And we talked through what the different ways to store sparse matrices are. Do you guys want to review that today, or how do you feel about it? Sorry, actually, is thumbs up for review or thumbs up as you feel good? Feeling good? Does anyone want to review it? Okay, yeah, I see some hands for reviewing it. So we'll just quickly take a look at it again. So the first one we saw was coordinate-wise storage, which I think is the most intuitive, where you've got a value, its row number, and its column number. And so you're basically storing these three arrays that has all your information. And actually, I guess first I should ask, what is a sparse matrix? Maria?
Zeros?
Yeah, sparse matrix has lots of zeros. And so not as many non-zero values. And I think sometimes more precisely, although this is a little bit flexible, people will say the number of non-zero values is scaling with n and not n squared, if you had like an n by n matrix. So coordinate-wise, I think is the most straightforward, and that's how we'll typically enter, kind of as a human, enter our values for a sparse matrix. Then one that was a little bit, I think, weirder when you first see it is compressed sparse row data structure. And here you're still storing the column number and the value, but you've got this row pointer. And the row pointer is just keeping track of when you've gone on to the next row. And so since we have, 0, 1, 2, 3, we've gone to the next row, 4, 5, 6, we've gone to the next row, 7, 8, 9. That's where this 0, 3, 6, 9 comes from. And the thing to note here, is there a relationship between 9, 22, and 1? Shake your head no, or nod your head yes. No, yeah, so I see a few shaking heads no. So this is a little bit confusing how they've written this here. But the 22 and 1 is referring to this entry here. And that has, not related to this 9. The only thing is if you look at index 3, this is telling us that the 9th entry, we've gone on to the 3rd row in a zero-based counting system. Or, starting from 0, we've gone row 0, row 1, row 2, row 3 for the 9th entry, but that has nothing to do with this value of 22. So it's a little confusing how they've written it here. We saw another form, which I think is confusing in a different way of writing it here, where they spaced out the row start index, to show you, but you're not actually storing those spaces. Any questions about the compressed sparse row format? So benefit of it is it takes even less storage space and also makes accessing your data by rows very quick and easy. However, you can convert between them. If you were primarily going to be accessing by columns, you would want to use compressed column sparse storage. And so some of this is kind of keeping in mind how you'll be using your data, and it's relatively efficient to change between these different formats. Yeah, so we saw this last time, and we used this to make our term document matrix down here. And actually, I guess we were feeding it into a CSR matrix. Okay, we saw how to display these as dense, and then I guess I left off with with an exercise. Was it this one of since the word? Okay, got it. Hey, does anyone want to share what they did? You got it? Can I give you the catch box, or?
Sure.
Good catch.
Okay, so what I did was, since that review came from the validation set, I took the valid term document matrix, and well, before that, I first looked at, I called string to int for late as the input, and got an index of 451. So then I know that, okay, I got to look at the 451st column in this validation document term matrix, and I knew that the index of this review was 1. So if I look at row 1, column 451 in the validation term document matrix, I get 2.
Exactly. Great. Thanks. Yeah, so look up the integer for late, get 451, and then you look it up in the validation term document matrix. I notice looking in here, this review has 144 tokens total and 81 distinct tokens. And we can get that from looking at this row in the matrix. It says this is 1 by 6010 with 81 stored elements. So next exercise, or first I should ask questions about that. how could you convert review.data back to text? And here, since we're using a text list, we have these nice kind of like helper attributes of review.data and review.text, but without just looking up review.text, how could you convert review.data to text? So take a moment to write the code for that.
I used the movie reviews I2S dictionary. Oh no, that's a list. Sorry. To convert all the integers to strings.
Exactly. Yes. Yeah. So use the list. You can do this inside of list comprehension if you want to get the movie review.vocab.I to SA for A and review.data. And then I think we have one more exercise. Confirm that the review has 81 distinct tokens.
You can get the distinct numbers through a set and then find the length of the set.
Exactly. Yeah. So get the length of a set. We'll tell you how many distinct ones. Oops. Well, thank you. All right. And so I just oh, I guess I have a little bit more. Here I show that, and I think we talked about this last time, that string to int is longer than int to string, since many words are mapping to unknown. And I was kind of just curious about what words were getting mapped to unknown. And so I wrote a little loop to go through the items and see if they map to unknown, put them in this list, just to see what they were. And here, remember, we've capped it at only having 6,000 words in our vocabulary. So a lot of these words are, words that probably do show up in many movie reviews. And later on, we'll switch to, right now we're just working on a sample of the data set. Later on, we'll switch to a larger data set and use a larger vocabulary. But I like doing some of these exercises of just making sure that you really understand kind of what the data means and how it's formatted and how you can ask little questions about it. I think is nice before you dive into the actual kind of computation that you're doing. Yeah, so to use Naive Bayes, and I guess I should check, have you covered Naive Bayes this year in other classes? Okay, I see lots of nodding. So hopefully you're familiar with this. We don't have to spend too long on it. We'll define the log count ratio for each word, and that's the ratio of the feature in positive documents over the ratio of the feature in negative documents. So we define our X and Y, our validation Y. And then here to calculate these log count ratios, we'll want to get the, is there a question? Want to get the words that show up in positive reviews and the words that show up in negative reviews. And kind of the number of times on average. So you can think like how often on average does the word loved show up in a positive review versus a negative review. And so that's what we're doing here with taking the negative reviews, and then X is giving us word counts from our term document matrix. What does np.squeeze do? If you have a nested array here, it's taking off kind of one of those nestings, and I saw some people doing the motion, kind of giving you a single array. So here we had this was, and really it's taking off a dimension, but in this case we're going from a array inside an array just to an array. So summing up the positives and negatives. So now I want you to compare how often does love appear in positive reviews versus negative reviews. So take a moment to write the code for that.
So for loved, I looked up the index of that with movie reviews vocab string index.
And then I just indexed P0 and P1 by that, since it's just the length of the vocab for all positive or negative documents. And that gave me the number of times the term was done, and the same for hated.
Exactly. Great. Thank you. Yeah, so it's just looking up the string to index for these words and then looking them up in P0 and P1. And so, and this is kind of a sanity check on your data. I would expect love to show up more in positive reviews. And let's confirm. Where did I find P0? P1 is positive, P0 is negative, and so yes, loved is showing up more often in positive reviews, hated is showing up more often in negative reviews. There are questions about that? So here we've really, just taken the counts of kind of how often these words show up in positive versus negative reviews. And then I was curious to look at an example of a positive review with the word hated in it. So just getting the integer for that token is 1977. I used np.argwhere to find which reviews have a non-zero value for that. Then saw, let me see, which of those were, then I got all the positive reviews and I took a set intersection of those two things. So got all the reviews that have the word hated, saw which ones of those were positive. It was these three rows for the movie reviews, and looking at one of them, it was interesting to see that this episode is extremely underrated. I love the unknown parts and the big twist at the end. I absolutely love that scene. For some reason, people have always hated the unknown episodes, yet I've always liked them. And so it's just kind of neat to confirm, like, yes, this is clearly a positive review, but it does have hated because it's saying how other people hate this. And then I did the same thing for finding a negative review with the word loved. I got all the reviews that have loved, all the reviews that are negative, took their set intersection, and looked at this one. I loved the first Izumi movie. I have to say that this movie was much weaker than I expected. And you can see how, this is a negative, even though they're talking about having loved a previous movie. Yes, Rebecca? Oh, can I throw you the text box?
Wait,
sorry.
Where do we get the 200 that we're indexing?
The 200? Oh. Okay, so I think I did this on the subsample set and then later had done it on the full set, so that may be an error. Well, yeah, I'm going to guess that that's from a previous time through.
So we could just plug in
plug in one of those numbers. Yeah, sorry about that. I have not been consistent, I think, when running the notebooks. Sometimes I am running the cells, sometimes I'm not. But use one of the numbers that shows up here in the set intersection, which maybe it's risky to try. Let me see. Okay, let's go on to applying naive Bayes, but that's just, I thought, a neat way to kind of also see, like, what does this P0 and P1 mean in terms of having these counts of words in positive reviews and words in negative reviews. I've just rewritten them here so you could see kind of all at once what they are. What we'll be doing is adding 1 to each, and this is just averaging over the number of positive reviews, averaging over the number of negative reviews, and we've added a 1 in the numerator and in the denominator to help with numerical stability for these. And then we take the log of their ratio. And I'll talk about, I've got a notebook 3B where we'll talk about, and we can do this briefly since you've seen Naive Bayes before, the derivation of Naive Bayes. But here I just wanted to use it and kind of see, does this make sense? I looked up the vocabulary most likely associated with positive and negative reviews. And I used NP-arg partition, which does not perfectly sort things, but it'll give you the number you request. It'll create a partition. So I wanted to get the top 10, the 10 biggest things and the 10 smallest things here. And so again, this is from the log ratios R that we've got here. And so these are the words that most most indicate that a review is positive or that a review is negative. And so I looked up BICO as being a positive word. And let me run this. And the kind of issue I ran into, I think with these, because we're still on the set of just the smaller sample, that some of these words only show up in one movie review, and so, but they show up a lot of times, and so that kind of colors it. But here I found a review of, this is a review of Cry Freedom, in which BICO is a historical figure, one of the main characters, very positive review. For negative, like I was curious about, Soderbergh is a director who's directed both good and bad movies, but in our subsample, oh, actually, I guess no, sorry. Let me see. Yeah, so I looked here and Soderbergh is only showing up in one of the reviews. So this is probably not, this would be more informative to do on our full data set, but I did find this person really did not like this particular Soderbergh movie. Although I think they even say in the review that he's done others that are better. So just a little bit more data exploration of kind of what is our log count ratios giving us. Yes? You don't have that in your, oh, okay. So if you don't have this in your notebook, that means that these are changes I did not copy. As I have two different copies of the repo, one that has the answers and more material than you have. I'll put the updated version in after this. Sorry about that. Let me make a note. Yeah, so always let me know. I try to copy over the updated versions for you, but if I forget, let me know. Although I think I didn't make too many changes, so I think from here on it's pretty good. So then getting back to Naive Bayes, you do want to normalize by, or not normalize, but define B to be the log ratio of the average number of positive reviews to negative reviews, kind of what percentage of the reviews are positive versus negative. And then we get our predictions by taking the validation term document times R plus B and saying, I think when those are greater than 0, we're predicting positive, less than 0, predicting negative. And we can check we've got 64% accuracy, which I think is reasonably good given that this was on a sample of our data using a pretty simple technique. Questions about that before we apply it to our full data set? Okay, so going to the full data set, you need to download that data and process it. And this is always, I would say, always start on just a sample of your data set when you're just figuring out what code you want to write, if your calculations work, because if things are slower on a large data set, you don't want to be kind of wasting that time while you're still experimenting. And so now we'll have a set of, I think, 25,000 reviews in our training set and 25,000 in our validation set. And then here where we're doing some processing that takes a little bit longer, so it's 4 or 5 seconds to get our term document matrices. It's often a good idea to save these so we can reload them later for quicker. Great, Naive Bayes on the full data set. So now we have 38,000 tokens as opposed to just 6,000. This will give us a much larger vocabulary. Go through the same process. Oh, here I ended up kind of formalizing what we had done before in looking at when words appear in negative reviews versus positive reviews, and just wrote a little helper method that gives you the ratio of, for a word, we convert it string to int, and then what's the ratio P0 to P1, where here P0 is the negative reviews, P0's the count of the word appearing in negative reviews, P1 is the count of how often it appears in positive reviews, and you can get a sense. Hated is much more likely to be in negative, 2 times as likely to be in negative reviews. Liked, anything less than 1 is more likely to be in positive reviews. Loved is even more disproportionately likely to be in positive reviews than negative, and so on. I just thought that was interesting to look at. Worst is almost 10 times as likely to be in a negative review as a positive. And did the same calculation before of adding 1 to P1 and dividing by the total number of positive reviews plus 1, taking the log. Here I was just looking at these R's. So this is kind of similar to this idea of before of taking a ratio. We've just added 1 and taken a log to help it be more numerically stable. Oops. I think I renamed it val term doc. And now we've got an accuracy of 80% for the full data set. So this is looking at a review based on the words, predicting if it's positive or negative. Questions? Yes? Yes, and we'll talk a little bit, I'll talk about numerical stability in a moment. But yeah, to avoid zeros, well, yeah, I guess it is just avoiding zeros in that case, yeah. And then the log is helping with numerical stability. So another variation we can take on Naive Bayes is Binarized Naive Bayes, which is maybe it only matters whether a word is in the review or not the frequency of the word. So previously we were looking at the counts of how often a word appeared in the review. Maybe that's not as important. So instead of keeping track of loved showed up 10 times in this review, now it's just going to be a yes or no, was loved in the review at all. To do that, we can just convert our term document matrix using .sign. And we get 82.9% accuracy. So this is even more accurate. And let me show you, actually, I guess I should show you just a little bit of So this is just a matrix of ones and zeros, telling you whether or not that word was present at all in the review. Questions about binarized naive Bayes? And this, before running it, I was not sure which would be more accurate. Like, it's not obvious to me that having a word, that the word frequencies don't matter. But it's definitely something worth trying, and that, yeah, in this case was more successful, or led to a higher accuracy. All right, so now we're gonna use logistic regression, and here the features are going to be, oh, Rebecca? C to I converts a class to an integer. So in this case, the classes are neg and pos, and this is letting us know if that's 1 or 0. Mm-hmm. That's a good question. Sorry, to repeat the question was when to use binarized versus regular naive Bayes. I would say often I feel like it's probably pretty quick to, once you've done one, to be able to try the other. But yeah, I don't have a rule of thumb on that. All right, so for logistic regression, so what's I should ask, and what's a unigram? A word, yeah. So it's just a word because it's and we'll talk about this more in a moment. An n-gram. We're going to be using n-grams to refer to a sequence of n words. Here's n is 1, so it's a single word. There are people that also, n-gram can also refer to characters, like at a character level, in which case it would be a single character. But for our purpose, we'll be looking at words. So here we can just fit a logistic regression to our term document matrix. We do have to convert the y values to be integers. I guess here, since they're classes, come up with a prediction, and we get 88% on this first try. So that's even better than naive Bayes. And the binarized version, so we went from 88.3% to 88.5% by switching to doing the binarized version. And so now we're going to move on and do kind of build on this to do something that will hopefully perform even better, which is to do a version of logistic regression with naive Bayes features. So for every document, we compute the binarized features as described above, and this time we're also going to use bigrams and trigrams. So here we're referring to sequences of words. So bigrams would be the dog said that, can't you? So any sequence of 2 words. And kind of by making this into a feature, like an obvious benefit is having things like not in there. You know, if it said, I did not love this movie, having not love is, you know, going to mean something very different than love when you're only looking at the individual words. So looking at this same movie review text set again, we're going to go back to the sample since we're doing something something new. Actually, I should run these. And so next what we want to do is we want to iterate through the sequences of words to create our n-grams. So we're going to kind of have to go through each review to get what are all the sequences of 2 words that show up. We'll do this with nested loops, and this can be helpful for the homework problem. This kind of has more going on than what you'll have to do in the homework. And we want to, kind of at the end, we're going to create a counter of what the n-grams were, how often they appear, and kind of in each review. And something to note about this is that this is going to end up being much larger than when we were just looking at individual words, since it can scale in a bigger way. So it's good we went back down to the sample data set. Actually, maybe this is a good time to take our break. So let's take a 5-minute break and be back at 12:05, and hopefully our matrix will be done being computed by then. All right, let's start back up. So we just finished computing our train n-gram, or our n-gram document matrix. So before we were saying term document matrix when our terms were just unigrams. Now we've got n-grams. So it's our n-gram document matrix for the training set. And here, note this has got 260,000 tokens. So a lot of tokens, because this can grow conceivably in like n factorial. You know, the fact that you can take all these different combinations. So let's take a look at what this looks like. I think I just randomly looked up 2005. Where did that come from? Well, let me look at, okay, so for I to n-gram, I was just curious about what's element 100,000, and it says the n-gram looks like this array of 2 things. So this must be a bigram with 2 words in it, 189 and 1301. And if I look up what words those correspond to, I get nothing changes. So it's conceivable that these 2 words were next to each other. So this is one of our bigrams. And here this is what corresponds to element 100,000. I look up another one, 100,010. This is 6348, which is has and. So that's another bigram. Here I find a trigram with index 6,116, and it's doesn't even is the trigram. There are questions about, and this is just to give you a sense of kind of like what is this matrix that we've found. So this matrix has, go back up, 800 reviews in it, and then it's got 260,000 n-grams, and it's a combination of some of these are unigrams, some are bigrams, and some are trigrams. And they're recorded as these arrays of 1, 2, or 3 things, but they correspond to sets, tuples of words with 1, 2, or 3 words in them. And they can be, you know, bigram, like nothing changes, or trigram, like doesn't even. Another trigram I found was look her usual, business and political. So just to kind of get a sense of what words appear together. Are there questions about this? Rebecca?
So what we're using just knows that like contraction
So here for tokenization, yes, I'll say most tokenizers will split up contractions into separate words. The other way they sometimes get split is, and we'll see this later, sometimes you just take the T off and have that as like apostrophe T as its own word. But yeah, that's a standard way to tokenize. And here I guess we're using the FastAI tokenizer, but in the regex lesson we'll look at how we could write our own tokenizer. Any other questions? Okay. So I did that with the training set. Now this is same code as above to make a validation matrix, which will also be a little bit slow. Really, I probably should have opened my saved versions of these. But yeah, since these are slower to calculate, you definitely would want to save them and then just load them in the future. All right, so, yeah, validation set has 200 reviews in it, same 260,000 token, or 260,000 n-grams that we're using. And now we can do naive Bayes on this in a similar way as to before. Here I'm just showing that the predictions look like this array of trues and falses. And now our validation accuracy is 76%. So this was a little bit, or not just a little bit, this was worse than what we had gotten with logistic regression. And ultimately what we're going to end up doing is using trigram features in a logistic regression to improve the performance. But this was kind of a way to get acquainted with having trigrams and bigrams. Do the binarized version of this. Oops. And again, the binarized version is a little bit, no, in this case, the binarized version is worse than the regular version. Questions on using naive Bayes with trigrams? All right, so now we're going to do a logistic regression where the features are the trigrams. So again, this will be having these sequences of words. Here we're going to use scikit-learn's count vectorizer to create our trigrams, and we give it, or create our n-grams, we give it a range. And so this is similar to what's asked for in the homework of saying, okay, I want you to give me the unigrams, bigrams, and trigrams back all together in this range. Notice it has you set a number of max features, which makes sense because these can get very large, particularly if you had a even wider range of what n-grams you were looking at. Yes? I believe this is inclusive, yeah. And we could check the... the documentation. Yeah, you'd have to look at the scikit-learn docs, but I believe this is inclusive. And the one in the homework asks for you. Oh, here it is. Yes. It's inclusive. All values of n such that min n less than or equal to n less than or equal to max n will be used. And this is, you can just hit Shift Tab or Shift Tab Tab to get documentation in a Jupyter notebook. Oh, and here I think I was just looking at the vocabulary of the vectorizer. You can see here a bunch of unigrams are still in there. Now we're in a section of bigrams. You can also, this can see how they add them, typically kind of by going through a sentence, and it's almost like you're, you know, like rolling a window over, looking at each combination of two words. Lovable self, self in this comma, which normally makes me. And the reason, you know, you're kind of taking what's the bigram, which normally is in kind of like the second spot, so then you slide over, you've got normally in the first spot, normally makes. So this sentence would read, lovable self in this, which normally makes me forgive her shallow acting, would be the sentence that this must have come from. If we go further, let me see if we get to, yeah, and then here we get to some trigrams in here too. Hard to believe she was the producer on this dog. So you can kind of see how the trigrams were constructed from the sentence. Questions about that? All right, binarized naive Bayes using n-grams from count vectorizer. Oops. Forgot to run this. So there I was getting 83% with the binarized version, 78% without. Let me go down to this part. Yeah, and so in the end, 83% is, I think, the best I did with the regularized logistic regression, where the features are the trigrams log count ratio. Other questions? Something, oh, go ahead.
Is I guess it would definitely vary from data set to data set, but like, how much do n-grams help in terms of like beyond trigrams or even, I guess, 4 grams?
Yeah, I mean, I would guess you probably rarely want, any that are too long. Something I mentioned in the intro that I haven't had a chance to look at yet is Sentence Piece, which is this library that does subword units, which is kind of a similar idea, I think, of looking at like character n-grams, but it's kind of pieces of words. And I know people that have used that kind of in conjunction with deep learning and gotten good outcomes. But yeah, I don't know of cases where people have taken like 6 grams or because the other thing is, as it gets longer, I think they're going to get more and more distinct. You know, they're probably like a lot of 7 grams that only show up once or something in the corpus. You're welcome.